Okay, so welcome along to today's exam revision Saturday session with Leaving Cert Chemistry. My name's Rob and I'm going to be bringing you through the next 40 minutes or so of this session. So we're going to begin. Apologies for the delay there. We had some sound issues, but hopefully we're back up and running now. To today's exam revision Saturday session with Leaving Cert Chemistry. My name's Rob and I'm going to be bringing you through the next 40 minutes or so. So, with apologies for the hold up there with the audio, we've got it working now, so we're good to go. Let's begin. So, with exam revision, I always start off my Saturday sessions. We all love discounts and special offers. So, for exam revision, for today up until tomorrow evening, we're happy to give you 20% off our standard or premium plans with the discount code rates20, and this can be used for subjects on the exam revision website. So I'm just going to bring you through the website very quickly, just so we can have a little look at it, and we can see that I'm just logged in here as a premium account. So this is what you will see is if you sign up for exam revision, a premium account with chemistry. So we can see when you log in, you have video tutorials, quizzes, presentations, PowerPoints, and we've got an exam builder, and we have the all-important H1 standard notes. So when you click into this, you'll see that Leaving Cert Chemistry is done out in all the units that there is on the Leaving Cert course, and there's also an exam preparation folder as well, which is filled with hints and tips for your exams. So once you click into units, then they're separated into different categories. So we have the oxidation reduction theory, oxidation reduction titrations, and we have electrochemistry. So if we look at the titrations, then you can see that we have our 5 titration videos ready to go for you. We also have an oxidation reduction titration self-correcting quiz, we have a PowerPoint presentation, and of course we have the H1 standard notes. So that can all be gotten on exam revision along with many of the other topics that we have, and we also offer a wide variety of subjects including junior cycle business, geography, maths and science. And you can see here we have Leaving Cert history, ag science, biology, business, chemistry of course my subject, economics, English, French, geography, Irish, maths and physics. So that is your quick whistle stop tour around the exam revision website, and don't forget you can use that code rates20. Also, I just want to point out to you, if you would like to obtain the notes from today's Saturday session, you can do so by signing up through the Google form that is in the description in the video below. We've got lots of upcoming Saturday sessions going ahead for the month of October as well. We've got Daniel with English on Saturday next week. We have Lee then with history on Saturday the 9th of October, followed by home economics on the 16th, junior cert Gaelga or Irish on the 23rd of October, and then maths to finish off the month with Anya as well. So keep an eye out for those. And of course, this is an exclusive for the Chemistry Saturday session. Later on in the week, we'll be announcing some revision courses for the October midterm. So stay tuned for an update on chemistry. We're still working on dates, but we will have all of the information out next week, and one subject will cost €99 to do. The revision courses will be 5 hours long. You'll be provided with all the notes as well that will be needed for the revision course. But the special offer is you can, if you pick to do 3 subjects, it will be €249, so you will save €50. And that will be valid until the 12th of October, and all of that information will appear on our exam revision socials and on the website later this week. So let's dive straight in. I told you we're going to do rates of reaction today, so let's get moving. We are going to today cover instantaneous rate and how we can find it. We're going to cover the factors that affect the rate of reaction. We're going to look at the rate of reaction experiments in particular, how concentration and temperature can affect rate of reaction, and also we're going to look at some exam questions on those experiments. So we can see here rates of reaction on Leaving Cert. I've just put together a little table, and we can see that it comes up quite frequently. Rates of reaction has appeared practically every year in the past 10 years. So the experiment on temperature appeared in 2014 and 2020. We can see that the concentration experiment appeared in 2017. The factors appear quite frequently as well, as does instantaneous rate and catalysis. Now, we won't be covering catalysis today. For catalysis, you can sign up to ExamRevision.ie and you will be able to access the notes on catalysis there. We just don't have enough time to cover it today. So let's dive straight in, and the first thing that's always good is to begin with a definition, set the tone, set the scene. So rates of reaction are used to describe how quickly or slowly a chemical reaction can occur. So a definition for rate of reaction: the rate of reaction is defined as the change in concentration per unit time of any one reactant or product. Now, that's an important definition that should be learned by heart. Chemistry is very specific when it comes to marking schemes, so you need to be word perfect with your definitions. The rates of reaction then, for a formula, you would have the volume of a particular reactant or product divided by the time taken to produce that reactant or product. So when we are talking about rates of reaction, we can have an average rate and an instantaneous rate, and there is a difference between the two of them. So your average rate is the appearance of a product over a specific time interval, where your instantaneous rate is the rate of the reaction at that particular instant in time. And it is instantaneous rate that is the one that is most frequently assessed at Leaving Cert. And you will be looking for instantaneous rate. So usually that would involve drawing a graph and then having to find the instantaneous rate of it. So sometimes students can find that a little bit difficult, so I've broken it down for you into a set of steps on how to calculate the instantaneous rate at a particular moment in time. So if you are calculating the instantaneous rate at a particular moment in time, you should always draw a graph. And usually it will be the product versus the time taken to produce that product. And what you'll do is you will draw a tangent. So a tangent, Anya will have gone through this on ExamRevision.ie. A tangent is a line which touches a curve at one point only. So you would draw a point at time x and then draw a tangent line. And we're going to do this in a second. And what you do is you would measure the slope of the line. So there's many ways you can do the slope. You can use the formula. We also have rise over run, which is the length of the vertical over the length of the horizontal. And once you calculate that slope, that is your instantaneous rate. So let's go and calculate the instantaneous rate for this graph here at 1 minute. So if you are finding the instantaneous rate at 1 minute, we can see on the bottom of our graph here that time is done in seconds. So the first thing would be that 1 minute is equal to 60 seconds. So we need to go and we need to find where 60 seconds is on the graph, and 60 seconds is somewhere around here. So I would say that it is at this point here. Now also, before you begin, apologies, you should have the line of your graph drawn in like that. Apologies, I should have that done beforehand. So as you can see, by looking at this graph, graphs can tell us a lot. We can see that at the start, the rate of reaction is going to be quite high because we can see the graph is quite steep in this first section, but as we continue on, we can see the graph starts to level off. So as the graph is starting to level off, it means that there is less of your products being produced at a specific point in time. So, back to calculating the instantaneous rate. So, to find the instantaneous rate at 60 seconds, what you need to do is you need to draw a tangent. Now, a tangent is something like this. That would be classified as a tangent for me. I'll take that as a tangent. So, a tangent is a line that touches the curve at one point only. So what you would do now is we will go and we will calculate the slope. Now to calculate the slope, usually I do the rise over the run. So if I'll do this in red just so that it's clear. So the rise over the run, I'm going to go and I'm going to do the rise over the run. Now you can do the rise over the run at any point on this graph, it doesn't matter. The slope will still be the same. Okay, but I'm just going to do it here. So I can see that this starts at about 140 and goes up to 200. So I know that the rise here is 60. And I can see that we start at 50 at this point here, and we go the whole way over to about 110. So I know that my change in volume is 60 and my time is 110. So we need to go now and we need to find the slope of this line, because the slope is what will give us the instantaneous rate. So if we go and find the slope, we know slope is rise over run. So I know that the rise is 60. Now where I got 60 from was, just to point out to you, I'll draw a little dashed line for you. So I went the whole way across here and I said that that was about 140 up to here, which is at 200. And then for my run, where I got 110 from was, I had 50 and I brought it all the way over to 110. So my run, actually, apologies, shouldn't be 110. My run should be from 50 to 110 is 60, apologies. So my run is 60. So my rise is 60. Divided by my run is also 60. And if we are to check that out and do the calculation, we can see that we are producing, at that point in time, we are producing 1 centimetre cubed of oxygen per second. Okay, 1 centimetre cubed of oxygen per second. So if I was to go and to do this calculation again, which I will, I'm going to say that we will go and find the instantaneous rate at another point in time. So I'm just going to clear the screen. Okay. And what we will do is we will do another calculation of the instantaneous rate. And this time what we'll do is we'll look for the instantaneous rate at 2 minutes. Okay, so if we look for the instantaneous rate now at 2 minutes. Okay, so let's look for the instantaneous rate. If we go now and do it at 2 minutes, we can use this same graph again. Okay, and we found that the rate at 1 minute was 1 centimetre cubed per second. So 2 minutes is, if we were to do it at 2 minutes, we know that 2 minutes is 120 seconds. So we would go to where 120 seconds is, and I'm going to assume that it's at about this point here. And we will draw a tangent to our curve at that point. So if we draw a tangent at that point, like that, okay, we will now go and we will find the slope of that graph. So the slope we know we can get using the rise over the run. So I'm going to start here and I'm going to rise, and then I am going to go over till I reach my run. So this is rise over run. So now my rise, this here is probably about 180, and this here is probably about 220. Okay, and then my run is starting at 100. So sorry, the rise there is 40. So my run is starting at 100 and going the whole way over to about 170. So I know that my run there is 70. So if I go again and I do rise over run to find my instantaneous rate, I can say that the rise is 40 and the run is 70. So if the rise is 40 and the run is 70, what that gives me is it gives me 0.57 centimeters cubed per second. So you can see that the rate at 2 minutes, at the 2 minute mark, we are producing 0.57 centimeters cubed per second. And if we take a look, we can see that this should make sense because the slope of my tangent at 1 minute, which was here, is greater than the slope of this tangent at 2 minutes. So that's calculating your instantaneous rate using the steps outlined. So the next thing we're going to look at is a short exam question, and this is 2018 question 7. So if you were to do this 2018 question 7, what you would do is you would go and you would draw out the two graphs that are here, and you would go and find the instantaneous rate. So I'm not going to do this because I've done an example in the last slide, but I will attach the marking scheme for you in the notes. Okay, so we'll move along and we'll now look at the factors that affect the rate of the reaction. So factors that affect rate of reaction, there's 5 of them. We look at the nature of the reactants, we look at the particle size, we look at the concentration, and we look at the temperature. We also look at the use of catalysts. Now today I'm going to go through the first 4 of them here. I'm going to go through nature of reactants, particle size, concentration and temperature. And if you want more on catalysts is completed on examrevision.ie, and you can sign up there for a premium plan, and you can use the discount code RATES20 to get 20% off. So if we're looking at the nature of reactants, the nature of the reactants is linked with the nature of them, or what they are. So reactions that involve oppositely charged species coming together is usually fast at room temperature. Now that should make logical sense. So oppositely charged species coming together, being fast at room temperature, it should be fast because opposites attract. So the positive will be attracted to the negative here. So the silver will be attracted to the chlorine because the silver is plus and the chlorine is minus, and that will give you silver chloride. Now this arrow pointing down here means precipitate. So it is silver chloride precipitate that is formed. Now, reactions that involve breaking of covalent bonds are usually slow at room temperature, because if you think about it, breaking bonds takes a lot of time, it also takes a lot of energy, so that means that the reaction will be slow. And an example of this is the reaction of ethanol with acidified sodium dichromate. And that is an example, and it is covered in organic chemistry on the Leaving Cert. The reason it's slow is because you are breaking covalent bonds, and this requires a lot of energy, so that will take time. Now, nature of reactants isn't a very common one to come up. The more common ones are the ones we're going to meet now. So if we look at particle size, the smaller the particle size, the faster the reaction. So this is because there is more surface area available. And how I like to explain this is I like to explain this using the idea of Barocca tablets. So if you have Barocca tablets, that is a whole tablet, then you have a tablet split into halves, or if you have your tablet split into quarters, like I'm showing here, you can see that in the whole tablet, the other reactant, or the liquid that the Barocca tablet, let's say it's water, the water can only access the Barocca tablet on the outside surface. Okay, same here with the halves, but the difference is with the halves, it's got the whole circumference of the Barocca tablet that it can react with, but it can also then react with the half bits here in the middle. So there is more surface area, or there is more side available for it to react with. Similarly with the quarters, it can react on the whole outer perimeter, but it can also react with the other sides that are now exposed because the Barak tablet has been split up. So that's why an increased surface area due to a smaller particle size leads to a faster reaction because there is more surface area available. So an example of this would be large marble chips in 50 centimeters cubed of HCl will take longer to react than small marble chips. The smaller marble chips will give a faster reaction because there is more surface area, as I've just shown on the previous slide. And this is shown lovely here in this graph. We can see that for the small marble chips, the rate is very, the slope of your line here is very steep. So that means the reaction is happening very, very quickly, and it levels off quite quickly. And you can see that the reaction is complete much earlier in your small marble chips than it is in your large marble chips. We can see here for the large marble chips the slope of the graph isn't as great, and that it levels off a lot later. So that's why we would say that the smaller particle size will give the faster reaction because there is more surface area. Okay, so if we take a look now at small particle size, often particle size can be linked to dust explosions, okay, and small particle size can often lead to dust explosions if the following conditions are present. Now your teacher may have done this in the lab with you with a chemical compound called glycopodium, so you can create a dust explosion in class using glycopodium if you have it in your lab. So with a dust explosion, the conditions that are needed for a dust explosion to occur, we need combustible dust particles, we need oxygen gas, we need a source of ignition. So a source of ignition, for example, would be a flame, whether it comes from a Bunsen burner, or a spark, okay, which could come from electricity. We need dryness, so you need to ensure that the container that they are in is completely dry, and as I've said, an enclosed space. So an enclosed space could just be a container. Now I often do this in school, outside with the students. We put the combustible dust particles in, we have a source of ignition, we have dryness, our enclosed space is just a biscuit tin, and then the oxygen gas we're able to get. So we're able to create a dust explosion, and that is a good way to show that small particle size can lead to a quick rate of reaction. So the next factor that we're going to look at is concentration, and changing the concentration of a reactant in a chemical reaction can alter its rate. And again, similar, we can say higher concentration means higher rate. So the higher the concentration, the higher the rate. So if we take a look here, we have 0.5 molar HCl, and we have 50 centimeters cubed of it reacting with magnesium. And you can see that it takes this yellow approach here, okay, where if we have 50 centimeters cubed of 1 molar HCl, we can see that it is much steeper at the start, so the reaction is much quicker, and again it gets completed a lot quicker. So we can see that the 1 molar concentration gets completed much earlier than the 0.5 molar. So the higher the concentration, the quicker the reaction. Now, we mentioned earlier that there's an experiment on the course for this, so that's what we're going to look at now. So we're going to look at the effect of concentration on the reaction of using sodium thiosulfate and hydrochloric acid. So this can be done using the X experiment method. So what we do is you would get a conical flask, and you would place the conical flask on a white sheet of paper with a red X or a coloured X underneath it. In the conical flask, you will put a clear solution of sodium thiosulfate. What you will do, you can see then that the cross will be visible underneath the conical flask from observation through the top. And once you add the hydrochloric acid, a cloudy suspension will start to form. And this cloudy suspension is a suspension of sulfur. And this cloudy suspension will cause the red cross that is drawn on the sheet of paper to become obscured. And as it becomes obscured, it obviously cannot be seen. And what we would see from an experiment is the more concentrated your acid is, the quicker the X will disappear. So usually what would happen is you would add 10 centimeters cubed to 100 centimeters cubed of your sodium thiosulfate, and adding 10 centimeters cubed, we would call this a 100% solution. So 100% would be 10 centimeters cubed of your HCl. What you do is you time how long it takes for the red cross to disappear using a stopwatch. And then what we will do is we will get 10 centimeters cubed of the HCl and 100 centimeters cubed of your sodium thiosulfate. That will be a 100% solution. So if we want an 80% solution, we can add 10 centimeters cubed of the HCl, but we can add 80 centimeters cubed of the thiosulfate and 20 centimeters cubed of the water. So we can see now that we are diluting down our sodium thiosulfate, so the concentration is less, so the reaction will take longer to complete. We can then consequently do this again with a 60% solution, which again would have 10 centimeters cubed of your HCl, but this time it would have 60 centimeters cubed of your thiosulfate and 40 centimeters cubed of your water. So here you can see that the concentration is decreasing each time. And what we should hope to see is that as the concentration decreases, the reaction will take longer to complete, so the rate of reaction will be lower. Then what we do is we would draw two graphs that would look something like this. You would have a results table, and in your results table you would have your concentration in one row, you would have your time, and then you would have your rate. Now it's important to know that rate, and I probably should have mentioned this earlier, to calculate the rate you do 1 over the time. That is how you calculate your rate. And usually in an exam they will either ask you to plot time versus the concentration, as we can see here, or rate versus concentration. And usually it is the rate that they get you to calculate or to plot, so you will get 1 over the time. So those graphs would be good to know and good to revise. So with rates of reaction, you should be revising how to draw graphs. That's very, very important. So some sample questions that can come up on this experiment. Okay, some sample questions. Describe the appearance of the suspension formed. So when the sodium thiosulfate and the hydrochloric acid mix together, they form a suspension, and this is a cloudy yellow colour, and that cloudy yellow colour comes from the formation of sulfur. So we are forming sulfur, so that's why it is a yellow cloudy suspension. Then it says, why is it important to use the same conical flask throughout the experiment? So you should use the same conical flask throughout the whole experiment to ensure accuracy and fairness, because we want to have a container that is the same size for this reaction to occur in. The flask should be rinsed out after each reading, and this should be done in order to avoid contamination, so that the next set of solutions don't get contaminated from your previous concentration. Then it says time and rate are said to be inversely proportional. What does this mean? So if something is inversely proportional, as one goes up, the other goes down. That's what inversely proportional will mean. So for inversely proportional, one goes up and the other goes down. So we can see here, this means that as the time increased, the rate decreased. So as the time went up, the rate got slower. And you can see that. You'll be able to see that through your graph. So that is your concentration experiment complete. So we're going to move on to temperature now. And with temperature, it is a very similar situation to your concentration experiment. So with temperature, the first thing that's important to know is that the higher the temperature, the quicker the reaction. So the higher the temperature, the quicker the reaction takes place. And the reason this happens is because there is more energy in your system. If you have more heat, the particles will have more energy to move around. That's something very basic from junior cert. If you have a liquid and you add heat to it, the particles can start to move around and that will cause them to change state, so the reaction can happen quicker. So higher temperature means quicker reaction, and that is because there is more energy. So by placing a solution of sodium thiosulfate and dilute hydrochloric acid on top of a sheet of paper with a red X, the hotter the solution, the quicker the red X will disappear, due to the solution turning a milky yellow colour. So if we go and actually have a look at this is the concentration experiment. We're looking at the effect of temperature on the rate of reaction using sodium thiosulfate and hydrochloric acid. So as you can see here, I've done out 3 different temperatures for us. I've done 40 degrees, I've done 50 degrees, and I've done 60 degrees. So the cloudiness will form quicker at 60 degrees because there is a higher temperature, so there is more energy for the particles to move around and react with each other. So again, we would have 10 centimeters cubed of hydrochloric acid and 100 centimeters cubed of sodium thiosulfate, and you would time how long it takes for the red cross to disappear using a stopwatch. You would repeat this for temperatures of 20 degrees, 30 degrees, 40, 50 and 60. And again, you would get a table of results, and one of 2 graphs will be drawn. It will be time taken versus temperature, or rate versus temperature. So we can see here I have the 2 graphs, and your results table would look as follows. So you would have temperature, you would have time taken, and then you would have the rate. So your temperatures would be 20, 30, 40, and you would fill that table in accordingly. You would also need to remember that to calculate the rate, it is 1 over the time. And in an exam, it's important to remember that because they won't tell you that the rate is 1 over the time. Okay, if they ask you to put together this table and calculate the rate, they won't tell you that it's 1 over the time, so you need to remember that. And again, the reason it's 1 over the time is because we've mentioned already that they're inversely proportional to each other. So we have discussed that already in the concentration. So these are your graphs, and you can clearly see here that for your rate, the rate of the reaction increases as the temperature increases. It's very evident from this graph here. As the temperature goes up, the rate of reaction increases, as you can see. So some sample questions for this experiment. They may ask you, what is the variable in this experiment? Your variable is temperature. Then it asks, why is dilute sodium thiosulfate used? So why would we use a dilute form of sodium thiosulfate? And it's to prevent the reaction from happening too quickly at higher temperatures, because we know as we increase the temperature, the rate of reaction also increases. So if we were using a concentrated form of your sodium thiosulfate, the reaction would happen too quickly. So give 2 everyday examples of temperature affecting the rate of reaction. So for example, a very good one of this is fridges. Fridges have cold temperatures, so they keep your food fresh because the bacteria aren't able to grow as quickly because the temperature is quite low. So they slow down, the fridge slows down the rate at which the food can decay. Similar one is catalytic converters in cars, and that's covered in the catalyst section on ExamRevision.ie. It says, why is the graph of temperature versus the rate is a curve, unlike the linear graph of concentration versus rate? And this is because temperature and rate are not directly proportional. Okay, they're not proportional. And then it says, name the gas given off when sodium thiosulfate reacts with HCl in this experiment, and the gas is sulfur dioxide. And that would be the same for the concentration experiment. So, as I promised, I said we would do an exam question, so here we are, we're going to do one now. This is the 2014 question 3 exam question, and this is an exam question based on the experiment for the effect of temperature on the rate of reaction. Okay, so let's begin. It says, as an experiment to investigate the effect of temperature on the rate of reaction between 0.05 molar sodium thiosulfate solution and excess 3 molar hydrochloric acid was carried out as follows. A timer was started as 5 centimeters cubed of acid was added to 100 centimeters cubed of your sodium thiosulfate, and a value was obtained for the time taken for the reaction to progress to a certain observable stage. The reciprocal of the time, 1 over the time, was taken as an approximate measure of the initial rate of reaction. So here they gave you 1 over time in the question. This procedure was repeated for a number of different temperatures, and the temperatures are shown below. So the first thing to do is they ask you to define the rate of the reaction. So to define the rate of the reaction, okay, we know that the rate of reaction is equal to the change in concentration of any one reactant or product per unit time. So that is part A completed. Explain the rate of reaction, and that is worth 5 marks. Now, the parts that you needed to have is you needed to have change in concentration. So change in concentration needed to be said, and you needed to also say per unit time. So those parts that are in bold there needed to be given fully in the exam, or you wouldn't get your complete marks. So that's right. Next is part B. Part B says describe and explain the change observed in the conical flask during the chemical reaction. So for part B, we would say that cloudiness or a precipitate will form, and that is for part 1. Describe. Now it says describe and explain, so you need to say where this precipitate comes from. So the cloudiness and precipitate forms due to the formation of sulfur, and I've mentioned that already in the experiment video. So for this to get full marks in this question, or in this first part, B part 1, you needed to say cloudiness, and you also needed to say that sulfur was formed. So cloudiness and precipitate were essential here, and the term sulfur. So this was for B part 1, and that was 3 marks for each part. So this was 3 marks for the words cloudiness or precipitate, and 3 marks for the formation of sulfur. Now for B part 2, okay, so for B part 2, it says describe how this observed change was used to obtain the reaction times. So this is basically asking you just to quickly describe what you've done. So any of the following is okay. So stand your conical flask on a cross. Time how long it takes for the cross to disappear. Okay, they are the 2 points that you needed for this question. So there was 3 marks for saying you stand the conical flask on a cross, and 3 marks for saying that you time how long it takes for the precipitate to disappear. So the next bit we have then is part C, and part C is asking us to plot a graph. Okay, so we are going to plot a graph now. So I'm going to try my best anyway to plot a graph for you. So it asks you to plot a graph of reaction rate versus temperature. So I am just drawing down my X and Y axis for you now. So I'm going to label these now. So temperature will always go on the x-axis, and then rate will always go on the y-axis. Okay, now it's important that you make sure that you label your graph fully. So temperature, you should put in the units, degrees Celsius, and the rate then is 1 over the time, and the unit is s to the power of -1. So you should have that labelled in all of the time. Next thing we're going to do is we've got our temperatures. So I'm going to go up in tens. So 10, 20, 30, 40, 50, and 60. And then our concentration starts at 0.0001 and goes all the way up to 0.05. So I'm going to go 0.01, 0.02, 0.03, 0.04, and 0.05. Okay, and now we are ready to go and we can start to plot our points. So at a temperature of 0 degrees, these are the two columns that we're using in the table. Just highlighted them there for you. So at 0 degrees, we have a temperature of 0.001. Excuse me. Okay, at 12 degrees, we have a temperature of 0.002, so you can see it's quite flat to start with. Then it goes up to 23 degrees, and it's 0.05. Sorry, 0.005. Next, at 30 degrees, it's 0.01, so now we're starting to get into the units that we have on our axis, which is good. Next is 39 degrees, and 39 degrees is 0.019, so that's up here. Next we have 47 degrees, and 47 degrees is at 0.003, which is up here. And then we have 57 degrees, which is up at 0.005. So your graph should look something like this, and I think I've done quite well with that. Now, a key thing for leaving Cert Chemistry, always use graph paper. Okay, always make sure you use graph paper. So the new Leaving Cert Chemistry booklets come with graph paper in them. So make sure you use graph paper when you are drawing a graph. Do not draw it on lined paper or blank paper. Use the graph paper that is given to you in the exam. Now, when it comes to marks on that graph, I'll do the marks in red just not to confuse you. So there was 3 marks for labels. There was 3 marks for the scales being drawn. There was 3 marks for having all of your points, and then there was 3 marks for having your line. So that graph was worth 12 marks. Then it says describe and explain the relationship shown in your graph between the rate of reaction and the temperature. So that's a lovely question. So this is part D. So for part D, we are looking at the relationship. So we can see that as the temperature increases, the rate of reaction increases. Okay, now it says describe and explain. So to explain this then, you would say that there are more effective collisions occurring. because the particles have more energy. So there was 3 marks for more effective collisions occurring and 3 marks for saying that as the temperature increases, the rate of the reaction also increases. The next part then is part E. Okay, and part E asks you to use the graph to find the value of the reaction time at 35 degrees. So you're being asked for the reaction time at 35 degrees. So what you would do this one in green, 35 degrees, so you will go up at 35 degrees until you hit the graph, and then you will go across and you reach a point here. Now what that is the rate. Okay, so part E, the rate at 35 degrees Celsius is equal to, I'm going to say, about 0.0145. Okay, seconds to the -1. But that is your rate. You have been asked to find the value of the time. So we know that rate equals 1 over time. So rate equals 1 over time. So if you were to rearrange that, we can say that time is equal to 1 over the rate. So that's what you're going to do. You're going to say time is equal to 1 over the rate, which is 1 over 0.0145. And when you do that, you will get around 69 seconds. So that year they took any value between 66 and 72 seconds. And the way the marks went for that was, I'm just going to do the marks again in red. So 3 marks for getting the rate and 3 marks then for going and figuring out the time. So it's important that you read the question very, very carefully and you figure out what they're actually asking you. Part F then is our last part, and part F says, what would the effect on the reaction times be if the experiment were repeated using 0.25 sodium thiosulfate? So we can see here for part F that for part F they are checking your understanding on concentration. And what we would say is, we would say that the reaction would be twice as slow. Okay, I'm going to put part F in here. The reaction would be twice as slow, and it said to justify your answer, and the reason for that would be that rate, what I would say is, I would simply say that the concentration is halved. Okay, because you can see that you go from 0.05 to 0.0025. So the reaction would be twice as slow, and the reason for that is because the concentration is halved. But if you want to take that a little bit further for yourselves and strive for that H1 answer, what you would say is, you would say that rate is directly proportional to concentration. Okay, and I'm just going to decrease the size of that so we can see it. So that is part F there. And when it comes to marks, there is 3 marks for this first part here that's saying the rate would be twice as slow, and then there is 3 marks for your justification. Okay, so that is a full exam question then on rates of reaction, and as you can see from earlier on in the session, it is quite common that these come up. So rates of reaction is a good question to have in your back pocket. Rates of reaction can come up in question 3 in section A, but it can also come up in questions 10 and 11 on the paper. So that's where I'm going to finish up with rates of reaction for today. So just to remind you that the discount code that you can use to access the ExamRevision website standard and premium plans for today is rates20, and that will expire on the 19th of September, which is tomorrow at 23:59. Also a reminder that we'll be launching our Easter revision courses over the next few days, so keep an eye on the website for the special offers, and of course for your Leaving Cert Chemistry date, if there will be one. We're still waiting to confirm that. And lastly, a reminder of the upcoming sessions that are still to come this month. We have English, History, Home Economics, Irish and Maths, and that will be followed by a week-long bundle of revision courses. So that's it for exam revision today. We will see you again next Saturday, and Daniel will be here to do some Leaving Cert English, and he will be focusing on Othello. So thanks a million for tuning in, and we'll see you